Welcome back to NCRT class 10th chapter number 13, magnetic effects of electric current. Children, after learning about electric motor, the next topics we are moving with the electromagnetic induction. This is very important, children. In order to understand electric generators, these concepts should be clear to you. Here, we are going to study about how a current is going to produce with the help of a magnets. Children, do you remember in the Oersted experiment, he did that when a current is flowing in the circuit means he absorbed that magnetism over there. He stated that a current carrying conductor produces magnetism property. So for this, the reverse possibility is also found by British scientist, that is Michael Faraday, children, isn't it? Here, what they did, that is, if a current carrying conductor is showing a magnetism property means a magnet can also produce a current. This is what reverse case for the Oersted experiment. This was achieved by a scientist, that is British scientist Michael Faraday in the year 1831, children. Michael Faraday in the year 1831. He stated that with the help of the magnets, we can produce a electric current, and he stated it as a electromagnetic induction. So, electromagnetic induction is nothing but the process of, understanding, children, the process of producing electric current when it is placed in a magnetic field. Means with the help of the magnets we are going to generate a electric current, and this has led to the discovery of children, that is electric current, that is electromagnets, electric generators, isn't it? And especially, children, power generation in the thermal stations is achieved, children. It has led to discovery of electric generators in order to produce current at power stations, isn't it, children? With this, we are going to produce a electric current in the power station with the help of a generator, children. So, how can we achieve this electromagnetic induction? There are two possibilities, children. One is, that is, moving a conductor in the place of a magnetic field. That is, we can achieve it by moving a magnet or coil, magnet into the coil, or moving a coil in a magnet we can achieve. And the one more method is moving a conductor, example, straight wire, rapidly between the poles of magnet. By these two methods, we can produce a electromagnetic induction. Children, in short, electromagnetic induction can be referred with the that is abbreviation EMI. It stands for electromagnetic induction. Is it clear, children? What is mean by electromagnetic induction? Who has discovered this? Electromagnetic induction is a process of producing electric current with the help of a magnetism. That is, with the help of a magnets. Isn't it, children? Then it can be achieved by any one of these methods. That is, moving a magnet into the coil, or moving a coil in the magnet, or moving a straight wire rapidly between the poles of the magnet. We can produce an electromagnetic induction. With this, we have the electric generators. That is, it has led to the discovery of electric generators, especially the power generation at the power stations we can achieve. And in this topic, we are coming with one more new word, that is induced current. Induced current. Children, what is mean by induced current? The current which is produced by moving a straight wire or a coil in a magnetic field. The current which is produced by moving a straight wire or coil, you can say, children, in a magnetic field is called induced current, isn't it, children? Understanding? Here we are moving a conductor in the place of a magnetic field. So produced current is called as a induced current. Understand? Induced current means when we move, that is, with the help of a motion of a conductor in the magnetic field, we are going to generate a electric current, and that electric current is called as a induced current. And one more we are coming under this topic, that is galvanometer, children. Galvanometer. Here, a galvanometer is a device, children. That is how we have voltmeter and ammeter devices in order to measure electric current and a potential difference. We have one more device that is called as a galvanometer. Here, the galvanometer measures or it detects the presence of an electric current in the circuit. What it will do, children? It detects, it identifies the presence of electric current. Isn't it, children? Generally, a galvanometer should be connected in a series, children. Isn't it? Often it is represented with the letter G. So, this is what a galvanometer symbol. And this device, generally, children, at the center you will find a pointer, that is at the 0 mark, we can say. So when a current is flowing in the circuit, means this pointer either it deflects to the right or to the left depending upon the direction of a flow of a current. Isn't it, children? This pointer starts deflecting either towards right or left depending upon the direction of the current in the circuit. Sorry, children. So you have to remember mainly 3 things here. The first one is electromagnetic induction means what? That is process of producing electric current with the help of a magnetisms. And induced current means what? That is the generation of an electric current by moving a coil in a magnetic field or moving a magnet in a coil, isn't it? An induced current is going to generate. And the next is galvanometer. It is the device which is used to detect a electric current in the circuit. Got it, children? So now we will study a simple demonstration of a electromagnetic induction. This activity consists of a simple things. That is, we have to take a coil of wire which has wounded with the copper wire, children, consists of a many number of turns and which is named as A and B. This is what? Coil, isn't it? And here a galvanometer is connected. First, what we have to do? For a coil, the 2 ends of the coil are connected to the galvanometer. Then we have to use a bar magnet such that this is what? Bar magnet. We have to place the north pole of the bar magnet towards the end B of the coil. This is called end A. This side is called, children, end A. This side is called end B. What we have to do at the very first step, after connecting the two ends of the wire to the galvanometer, we have to do at the first case number 1. You can note it down, children, isn't it? We have to bring the north pole of the bar magnet towards the end B of the coil. That is, when we bring a north pole of bar magnet towards end B of the coil, we have to observe changes in the galvanometer. So children, what happened when we bring a north pole of the bar magnet towards the end B of the coil? It has experimentally found that, children, this galvanometer started deflection. Understanding, children? This pointer has deflected towards right. Means it has shown a momentary deflection. It has deflected to right and immediately it comes back to the 0 mark. So what happened here? The galvanometer shown momentary deflection. Towards right, isn't it, children? So the pointer of the galvanometer, what it did, it has deflected towards right. When it is obtained, children, that is when we brought a north pole of the bar magnet towards the end B of the coil, the galvanometer has deflected towards right and again come back to the 0 mark. So here, why it is deflected, children? Our question is, why it is deflected? Isn't it? The function of a galvanometer is to detect an electric current. So it is clear with its deflection that there is a generation of an electric current here. Isn't it? Okay, next we will continue to the step number 2. Case, you can say, what we did now, we have to take out this north pole of the bar magnet from the coil. Understanding, children? First what we did, we have inserted, means brought the bar magnet towards the end B. But in the second case, we are taking out, that is, we are taking away the bar magnet from the coil. Isn't it, children? That is, when we take away the north pole of bar magnet from the coil, once again the galvanometer has deflected, but to the opposite direction. Initially it has deflected to right side, but when we are trying to take out this bar magnet from the coil, children, it has deflected towards opposite side. Means this is what left and this is what right. Initially it has deflected to right. That is when we brought a bar magnet into the coil. But what we are doing now, we are taking out the bar magnet from the coil. So it has deflected to opposite direction, that is to the left side. That is, when we take out the north pole of the bar magnet from the coil, the galvanometer deflected towards left direction. So here once again confirm that there is a generation of an electric current. That it means that an induced current has set up here. Isn't it, children? Or this is all at first and a second case. Means with the help of a motion of a magnet, we can conclude that there is a generation of a electric current. So now in the next step, what we are doing, we are keeping the bar magnet we are bringing a coil towards the north pole of the bar magnet. Understanding, children? At step 3, what we are doing? Keeping bar magnet stationary. The coil is brought near, that is, the end B of the coil is brought near the north pole of the magnet. End B of the coil is brought near north pole. Means then galvanometer has deflected towards, once again, right, children, it has shown momentary deflection again here. And similarly, when we take out this coil away from the north pole of the bar magnet, that is, when we take out the coil away from the north pole of a magnet, once again the galvanometer has deflected to left, isn't it, children? That is here G, nothing but a galvanometer has deflected towards left. So it is clear that, children, by bringing a magnet towards the coil or by bringing a coil towards the magnet, we can generate an induced current. So here, one thing we have to note it down, children. When both the objects, that is, when the coil and the bar magnets are both at stationary, means at rest, no change in its displacement. That is, at stationary means there is no deflection in the galvanometer. So moving a coil or moving a magnet only, we can bring a electric current. So when both these are at stationary means there is no current. So because of that reason, the galvanometer has not shown any deflection. So dear children, from this activity, we can conclude that whenever a magnet or a coil is brought towards, that is a coil, and induced potential difference will set up in the coil and it will result into the generation of a what? Induced current. That is due to induced potential difference and induced electric current can be obtained, children. So is it clear? Now induced electric current, how it is obtained, children? Either by bringing a magnet towards a coil or by bringing a coil towards a magnet, children. So we can produce what? Electric current. And even, children, by changing the polarities of the magnet, you can observe and the result is same, but you will get in a opposite directions, children. So from this activity, we can say that by moving a magnet into the coil or bringing a coil towards the magnet, we can produce an induced electric current. This was discovered by Michael Faraday. He was a well-known British scientist, children. In the early days, he had no formal education, children, but he used to read the books which actually he is used to work in a book binding shop. Whatever the books coming for a binding, he used to work those books. And by doing so, he got an interest towards reading the books, and he got an interest towards the science subject, children. And one fine day, he got an opportunity to listen the lectures of Humphrey Davy, who was working as a great lecturer in the Royal Society at that time. So very soon after listening all his lectures, he has written about his ideas to the Humphrey Davy. And very soon after looking into those ideas, Humphrey Davy, he made as assistant to his laboratory, isn't it, children? Davis Royal Institute's laboratory. Very soon only, that is Michael Faraday became a assistant, and from there he did many experimental works, and he did very great discoveries there, we can say, children. And he he was the first scientist who with experimentally proved that electromagnetic induction, and it has led to the generation of electric generators. And further he also stated there is loss of electrolysis. This is all about, children, a simple story and a demonstration of electromagnetic induction. Is it clear, children?